1. So let's make it simple maybe. L1 is equal to L2, for example. Okay, somebody answered. Thermal conductivity, K. Uh, I'm not sure, but hopefully it's correct. Okay, so this is the, again, element 1 and element 2. So what is the global? Remember K capital for the global. And so, okay, in this case, we know that this is going to be K1, L1 minus K1, L1 minus K1, L1. But here, because of the element connectivity, we know that this is going to be K1, L1 plus K2, L2 minus K2, L2 minus K2, L2, K2, L2. And of course, this is going to be 0 and 0, 0 and 0. So this is the uh, element conductivity, global, uh, global connect, thermal conductivity matrix, matrix. All right, so take note that my diagonal is positive. If you get a negative in your diagonal, then recalculate. Something is not right. Okay, because the requirement, syaratnya, is that K, your diagonal, must be always positive. Must be always positive. All right, so that's for the global uh, conductivity matrix, and let's look at the uh, heat rate. Heat rate vector. So heat rate vector is this one. Okay, this one is for the element. So note Q is the same, and L1 and L2. So in this case, what you can see here is that for global, so this one is uh, global heat conductivity matrix. So now this is the global heat rate vector. Okay, so what we have here is, of course, our capital, sorry, our R, uh, capital R. Remember that the convention is always small is for the element, small r is for the element, or small k is for the element, where the capital of that is for the global. So in this case is RQ is again, so in our case, this is just QL over 2, QL over 2. If the element has a different length, then Q over 2 is the same. Then we have L1 for element 1 and L1 plus L2 because this is the conductivity, and L2. Okay, so this is what we get. This is what we get. So now the next thing is to do the assembly. To do the assembly, and of course assembly. So what we call is SLE. So note that I think by now you should know that RQ1 is just QL1 over 2, 1 and 1, and R small r. This is element 1. This is element 2. Is QL2 over 2, 1 and 1 and 1. So the assembly is just this. Sorry, the global is this. So in our solid mechanics problem or structural problem, it is just K times Q equal to F, right? So in the case of heat transfer, what will it be? What will it be? So note that in this case, K is our element stationarity and Q is the unknown DOF, right? The unknown DOF. and this is the force. This is the force. So for heat transfer, what are the unknowns for heat transfer? What are the unknowns for heat transfer? So for the unknown for heat transfer is our temperature, right? Our T. And we know that this is our R, our heat rate vector, our heat rate vector. So this is the matrix. This is the matrix. So in this case, if we do this, okay, we can have this. Let's say we do this. Let's say we do this. So this is going to be K11, K K21, K31, K12, K. Oh, sorry, this is all capital K. Susah nak tulis dengan tangan, bezakan huruf kecil dengan huruf besar. So let me stress that this is capital K. This is capital K. Again, capital K. Capital K. Capital K. Okay, and of course, T1, T2, and T3 equal to R1, R2, and RT. Note, this R is not reaction. This is not our mechanics problem. This is heat transfer problem. And take note that something else here. Okay, so this is my T1. Okay, note 1. So this is T1. Let me put this up here. So we have K1, we have K2, and this is our T1, our T2, and our T3. Okay, look at this. What would we do after this? Okay, so we assemble the SLE, the global SLE. So what's next? What's next? What's next? In the case of solid mechanics, what do we have to do? Can you solve for T1, T2, and T3 in this case? Anyone? Can we solve for T1, T2, and T3? Okay, let me rephrase the question now. Let's say we have K, and then we have Q1, Q2, and Q3 for our solid mechanics problem. So, and then we have F1, F2, and F3. So can we solve this problem? What do we need? What do we need here? So after we assemble everything, our K matrix, our heat rate vectors. Okay, so somebody said we need boundary conditions. For in this case, for example, in our bar problem, for our bar problem, I think the first time that we did, we have this, right? We have this. So we fix. So we know that Q1 is equal to 0, right? Q1 equal to 0. Then we can solve this problem. Okay, let's look at before the boundary condition. So let's say this is our bar. Let's say this is our bar. And we are trying to solve this. We are trying to solve this. We are trying to solve this SLE. And we see that, okay, we have Q1, Q2, and Q3. Note, what's the problem here? Why can't we solve this? Why can't we solve this? Because it has no boundary condition here. So remember in your static, we need somebody to hold in this case, this bar here. It need to be, because it is static, right? So it must stop. So in this case, it can go either way. So that is why we need to basically anchor this and fix it to the wall. So now we can solve this. So the same thing with this heat transfer problem. So we cannot solve this because we do not constrain this. We do not know what are the boundary conditions. So this is special. This is special. So in this case, in the case of our bar problem, we need at least one boundary condition so that we can solve the problem. For example, I think what we did last time was Q1 equal to 0, right? The rest, uh, so we have two unknowns here. So we do not know this. So we solve for the equations because it's a 2 by 2 matrix now. Once the boundary condition is known, then we have only 2 by 2 matrix, then which means we have two equations with two unknowns. We can solve it. And again, if you recall correctly, I think some of the equation, the problem we have, for example, Q3 is being restricted. Okay, Q3 is, for example, this thing is Q3, then we say Q3 is maybe limited to maybe 1.5 mm. So again, this is what we call the homogeneous boundary condition, and this is what we call the non-homogeneous boundary condition. So, but we need at least one boundary condition for this solid mechanics problem, right? But in this case, remember, okay, for in this case, we still need to have boundary condition before we can able to solve for the unknowns here. So how many boundary conditions do we need here? How many boundary conditions do we need here? How many? We need one. Okay, for solid mechanics, we need at least one. Okay, so in this case, in my example here, this is the one boundary condition. This is the second boundary condition. So in this case, this is what we call the homogeneous boundary condition. This is the non-homogeneous boundary condition. So in this case, one is enough to solve this kind of problem. Okay, for solid mechanics problem, for bar element problem. But for heat transfer, note that when we derive this, we notice that the governing equation is a second order ODE, a second order ODE. So a second order ODE which requires two boundary conditions in able to solve. Because for example, kalau kita ada, for example, uh, if you if you have for example, if you integrate a second order equation, you notice that you have C1 and you have C2 to solve, right? Saya nak bagi example tapi uh, tak berapa clear ni. Sekejap So, okay, second order basically requires two conditions. Again, it slipped my mind. Saya tak ada contoh kat sini. But again, when you integrate a second order equation, okay, you need to have two conditions because the first time you integrate, you have plus C1, which is one unknown. And the second time you integrate, then you have uh, C2, another constant. So there are two constants that you need to solve because there are because the equation is a second order equation. So how can you solve C1 and C2? First constant and second constant. So you need two boundary conditions or you need two conditions. So in this case, this is a second order ODE and it requires, note that this is a second order, okay, because in order to solve for T, in order okay, now I get it. So for example, we have K d square T dt dx square. So K is a constant. So the first time you integrate, uh, 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 let's wait for a while. Okay, the first time you integrate, Okay, you have k dt dx plus c1. Okay, the second time you integrate, because you want to solve for t, right? You want to solve for t. So the second time, to solve for t, you integrate one more time. Then you have k t as a function of x plus c1x plus c2. Okay, so these are the unknowns here. And you need to have two conditions. In this case, we need two boundary conditions. We need two boundary conditions. All right, so that is why in this case here, we know that this is a second order ODE requires two conditions to be able to solve for our t, for our unknown t here. Right? That's the idea here. That's the idea. So one condition is not good enough, but we need two conditions. Yeah? We need two conditions. Okay, we need two conditions. So note that the SLE is K. Again, this is should be capital K, 1, 1, K, 1, 2, K, 1, 3, K, 2, 1, K, 2, 2, and K, 2, 3, K, 3, 1, K, 3, 2, K, 3, 3, and T1, T2, and T3, and equal, of course, R1, R2, and R3. Note, this is a 3 by 3 matrix, and it requires two boundary conditions, which mean this is easy to solve. This is easy to solve. But if you look at this kind of problem, normally you have at least 4 nodes. 3 nodes is too simple for you to solve. Okay, I'm using only 3 nodes because I need to show you how we get the boundary condition. So let's look at this equation. So what is the boundary condition? What is the easiest boundary condition here? What's the easiest boundary condition here? Anyone? So again, this is our, we call composite wall. This is K1, small k, because this is element K1 and K2, which is element 1 and element 2. So we have T1, T2, and uh, we have T1, T2, and T3 here. Okay, so one way is just to note that we need at least two boundary conditions in this case to solve the problem. So we can assign, or we know the value of t at, let's say, at node number 1. So now, let's say t is known. Let's say t1 is equal to alpha. So now, one boundary condition is met. So now let's rewrite this. Let me change pen here. Change color. So now we know that T1 is equal to alpha. T1 is equal to alpha. So there's no use to have 3 equations because there are 2 unknowns, which is T2 and T3 now. Okay, T1 is already known. So we know that this is equal to alpha. T1 is equal to alpha. So we know we are not going to use this equation. Okay, there's no need. Now we have 2 equations and 2 unknowns. But before that, recall that T1 uh, is not equal to 0. T1 is not equal to 0. And because of that, what we have here, we need to do this. We need to do this because this column here must be times T1. Or simply, if I rewrite this, then it will become something that look like this. So K22, K23, K32, K33. Note that T1 is already known, equal to R2 and R3. Now, because of when I eliminate the first equation here, I need to do something, which is, because this is on your left-hand side, I need to bring it to the right-hand side, which is now minus T1 times K21 and K2, K31. Okay, if you are not confident with my math here, what you can do is you can just uh, expand this. Expand this K1. Okay, so let's say this is K11 times T1 plus K21 times T2 plus K31 times T3 equal to R1. But T1 is already known, right? So this simplify as K21 T2 plus K31 T3 equal to R1 minus K11 times T1. Uh, Oops. Oh, no, I get something not right here. Okay, sorry. I'm using equation number 1. I should not use equation number 1. I should have used equation number 2. So equation number 1 is not being used. Okay, so this is not used. So let's try the second equation, which is K21 times T1 plus K22 times T2 plus K23 T3 equal to R2. Note that now T1 is known, right? So we put it on the right hand side. So now this is K22 T2 plus K23 T3 equal to R2 minus K11 T. Not T. This is K21, yeah. So 21 times T1, which is the same as this, right? Which is the same as this matrix form. K22 T2 plus K23 T3 equal to R2 minus T1 K times K21. Okay, so this is just a simple manipulation sahaja, a simple manipulation. But note that in this case, again, the requirement is that we must have two boundary conditions, not only one, because the governing equation says so. Okay, the governing equation says so. Remember that. Remember that. This is from the governing equation. It's a second order ODE. So second order ODE requires two conditions. In this case, two boundary conditions. So we need another one. So for example, now we know that let's say we know that this is T T3 equal to let's say beta now. Let's say beta. And again, let's say now let me change color. Okay, so because T3 is known, then so we say we are not going to use this. But note that this column is being multiplied with T3. So now we need to do something else. We need to do something else. So if I write it here, so let me use my red pen here. Okay, minus. This is just minus. Uh, Sorry. Minus. Uh, Minus T1. K K11, K21, K31. But note that this is not This is not used because the first equation is not used. And then we also need to change blue color here because of this minus T3 K31 K32 K33. And again, this equation is not used. Okay, and for the first equation, this is not used. So finally, we can find, because there are two unknowns, sorry, there are three unknowns and two boundary conditions. So we are left with only one unknown, which in this case only T2, yeah, only T2. So if you look at this now, we can simply find what is K2, sorry, T2. Okay, so now if we consider this equation, then this bottom one, this equation will not be used. Okay, this equation will not be used. And this equation, this column, okay, is also not going to be used, but we need to put it on the other side. So in this case, we know that K22 T2 equal to R2 minus T1 K21 minus T3 K3 T3. Betul tak? Okay. Minus T3 K T3. So this is the equation now. So do we know what is K22? Do we know what is K22? Yes, because all these are the coefficients, right? These are the coefficient matrix. So this is the, this has this value, this k values. Yeah? So we know all the k values here because this is the, what we call the coefficient matrix. Yeah? Coefficient matrix. So because of that, can we solve for T2? So T2 is just R2 is known, T1 is known, K21 is known, T3 is known, KT1 and T3 is the boundary conditions. T1 and T3 are the boundary conditions. So this is T3. KT3 is the coefficient, then divide by K2, 2. Okay, because there's only one unknown. So this is very simple. But if you have this kind of wall, then we have T1, T2, T3, and T4. So even though there are 4 nodes, but remember, we need to have 2 boundary conditions. So we have 2 unknowns. So a total of 4 degrees of freedom in this case, but there are 2 known values or 2 boundary conditions. So what we are left of are the 2 unknowns. So this one you have to use matrix lah. Okay, so this is 3 layers. 1, 2, 3. So 3 element, 1, 2, and 3. So but 2 elements, very straightforward. 2 elements is very straightforward. So one boundary condition is what we call. So in this case, our BC is what we call the specified temperature. Temperature is specified. So let me take a look. This is what we call a specified temperature. So one boundary condition, one type of boundary condition is temperature specified. Kita dah beritahu dia. This is what we call the temperature specified. So kenapa ni? Okay, temperature specified. Something wrong with my pen here. Okay, so in this case, we know what is the T value. For example, T equal, for example, T alpha equal to alpha. Okay, so this is the temperature specified. Temperature specified. So this is one kind of boundary condition. So the other one is, for example, is what we call the convection boundary condition. What is convection? What is convection? So note that when I think the first time when I give you this lecture, we have what we call three modes of heat transfer, right? We have conduction, we have convection, and we have radiation. So I mentioned to you that we do not cover the radiation because it's a I think it's a third order. It's a third order ODE. So okay, so we do not cover that one. Okay, we do not cover that one. So, but take note, it can be done, but it is just not covered in this class. Okay. So convection. So let's look at the governing equation. Sorry, let's look at the some of the physics. In this case, for conduction. So this is one mode of heat transfer. So let's go for conduction first. I just want to show you the equation for conduction. So Q, heat flux for conduction is just minus K dt dx, right? So this is what we call conduction, uh, conductive heat flux. Conductive heat flux. So basically, conduction is in, for example, we have a metal bar. So the heat flow from, let's say, hot area to cold area, right? So the heat transfer happens in the same material, same medium, same medium. Mediumnya ialah dalam kes ni ialah, let's say, metal. So it's same medium. So normally this is what we call same medium. Note that this is the change of temperature with respect to the length or the distance, dt dx, and this is the somebody mentioned k was what was k just now. Let me look at chat box. Thermal conductivity coefficient. Okay, now convection. So convection, we have convective, okay, convective heat flux, which is H T L minus T alpha. Okay, now this is different medium. What is meant by different medium? For example, the heat dissipated from this metal to the air. Okay, so from metal to fluid, from metal to air. So these are two different mediums. So this is convection. This is convection. So note that it has the same form of equation. So this is what we call the convection heat transfer coefficient. So this is convection heat transfer coefficient. Okay, and note that this is the difference in temperature. Difference in temperature. This is again difference in temperature, dt dx, and this is the material property, and this is what we call the fluid uh, properties. So air is a form of fluid. So fluid mechanics, for example, fluid mechanics kita belajar not only in air, kita belajar air kan, fluid mechanics, or especially orang aero. Actually aero students, their fluid is air. Okay, their fluid is air. So maybe for orang lain, fluid dia might be some chemical or some water. Orang kapal, orang marine, the fluid mechanics is of course air laut, for example. Okay, so this is the property. So now let's look at the second type of boundary condition. So how do we put this boundary condition? So let's say this is my let's say this is my so let's say this is my again my element. So I have T1, T2, T3, and let's say T1 is known as alpha. Okay, so okay, this is K1, this is K2, and now what we have here, this is our T3, T3, and what we have here is, let's say we have kipas angin, we have a fan here that blows the air. Okay, so the property is H and the temperature is T, alpha. Sorry, T infinity, which is the ambient temperature. Let's say the ambient temperature in my room is about 25 degrees C, but maybe this is 100 degrees. Let's say alpha is 100 degrees. So maybe this here is 80 degrees, and here maybe 60 degrees, and T alpha is, sorry, T infinity is 25. So what do you think will be the temperature at on this surface here? Will it be 60 or will it be less than 60? Of course, it will be less than 60 because we have a fan that cools the surface here. So how do we put this? How do we put the boundary conditions here? So let's see let's see uh, our global coordinate, sorry, our global K matrix here. Okay, let me delete this. I don't think we need this. Okay, so K21, K22, K23, K31, K32, K33, and we have T1, T2, and T3 equal to R1, R2, and R3. And of course, because just now we know that T1 is alpha, then the equation becomes K22, K23, K32, K33, T1, oh sorry, not T1, T2, and T3 equal to R2, R3 minus T1 times K21 and K31. Okay, so this is after we apply the boundary condition for T1 or the left wall. So now, how do we put this? How do we put the second boundary condition here? How do we put this boundary condition? So note that this is let's say this is your wall, which is a solid. Maybe this is aluminium, this is copper, and then this is air. Okay, this is air. Okay, so three different mediums here. So metal, solid, and then air. Okay, so note that our Q is H TL minus T alpha as T infinity. So in this case, our TL is just our T3. So this is T3 because the last medium is our T3, the wall where T3 is measured. So this is T3. So note that how can we put this into our governing equation here? Okay, how can we put this into our governing equation here? Okay, is T3 known? Where is T3? T3 is here, right? So this is on the left-hand side, right? This is on the left-hand side. So we need to put H times T3. So let's do this. So let me redo this. So K22, K23, K32, K33, and then we have T2 and T3. We need to include H with T3. So what we can do here is plus H. Note that now H is included for at least this part here. And because we have put this thing here, so we also need to have, we have the right hand side, we also need this one on the left hand side, this T infinity here. So let me change color here. Let me change color. So this is our H. Okay, and then what we have here is R2, R3 minus T1, K21, K P1, and we also need to have HT3. So how do we put that? How do we put that? So in this case, what we need to do is we need to have a plus. Okay, let me put the blue color here, and plus 0 and HT infinity. Okay, now this contributes is equivalent to this here. So this is just HT3 on the left hand side minus HT infinity on the right hand side. Okay, so this is what we get. This is what we get. So now, can we solve for the problem here? So H is known, H is known, KT3 is known, H is known, T infinity is also known. So can we solve for T2? Yes, we can solve for T2 because all these element in this T, in this K matrix here are known. The values are known. Okay. T3, T3 is not known. Okay, so you need to solve for T2 and T3 now because you have two equations with two unknowns now. But this is known. This is known. So these two, R2 and R3 are known. T1 is known. K21, K31 are also known. Is known. So all these are known values. All these are known values. So we have two unknowns with two equations. Can we solve for T2 and T3? Of course, we can solve for T2 and T3. So that's the second boundary condition. Okay, that's the second boundary condition. So we have one more boundary condition. So this is the first type. This is the second type. And the last type is another one is just similar to what we call your point load. Point load. So in this case, this is what we call the heat flux. Heat flux. For example, uh, for example, we have, I'm running out of time. I'm sorry, I have to go very quickly here. So let's say we have our T1, our T2, our T3, okay? And, okay, so we also have, let's say Q. Let's say Q, let's say Q. Let's say we have, let's say Q, Q naught at T, uh, sorry, uh, let's say we have, okay, let's say we have Q naught here. Let's say we have Q naught at this side here. So again, our K matrix is K and T1, T2, and T3, and our R1, R2, and R3. So this is just like your bar element, right? So this is your force, this is your unknown, this is your coefficient matrix. And how do we put point load in our bar element? So basically, we just put point load. In this case, our point load here is just Q naught, 0, and 0, because Q naught is only applied at node number 1. So that's it. That's it. So these are the three types of, missing, yeah. These are the three types of boundary condition that we have for heat transfer problem. Heat transfer problem. I'm sorry, my PC is acting up again. So hopefully you get what I meant. Hopefully you get what I meant. So I think that's it. I think that's it for now because I already took your 10 minutes time before I think this is your lunch time. All right. So thank you very much, everyone, for joining. See you again on Wednesday. On Wednesday. All right. Thank you very much.